All right, guys, we're going to get started today on section 6.2. This is taking us from the concept of a Riemann sum to a integral. And as I'm looking at this, this is kind of just, if I give you something or if you are given something in sigma notation, can you turn that into an integral? So in my opinion, this is kind of a narrow scope of things to learn, but we won't take too much time on this one. So let's get going with our work. We start off with a set of instructions. Number one is to factor out the candidate for dx. Almost always you're going to be using dx as 1 over x, or 1 over n in this case. So we take our expression here, we factor out a 1 over n from our 1 over square root of n cubed, and that simplifies this really nicely in the sum. Notice that. The next part, what they're calling step 2, is to identify the x values, and the x values are the things that are changing in here. So that's 1 over n, 2 over n. You notice you have them here, 1 over n, 2 over n, all the way to n over n, which means that your x is some k value over n. K being the variable that changes as an index. So 1, 2, 3, 4, 5. Okay. The next part is to find the range of x values as n approaches infinity. So we're going to take this first term, 1 over n, and we're going to find the limit as n approaches infinity. And as n approaches infinity, you notice that 1 over n goes to 0. The next thing is to find the upper limit, and you're going to take this upper bound, n over n, and you're going to say what happens to n over n as n goes to infinity. And you'll see as n goes to infinity, n over n will just go to 1. That's our upper bound. Now we know our integral is going to go from 0 to 1. Step 4 is to verify that dx is a correct candidate. Basically, 1 minus 0 divided by your highest n should be equal to your dx. So in this case, you got 1 over n, 1 minus 0 over n, and that agrees with the dx that we isolated over here, 1 over n. And lastly, we're going to figure out what f of x is. The summation in term contains root 1 over n, root 2 over n, root n over n. And so our f of x should be root x. Remember that these are all proxy values for x. So f of x is root x. So in other words, we get the Riemann sum integral from 0 to 1 of root n dx. And that's a typo. That should be root x dx. There are a couple of typos that I isolated here in this problem. Let's see how that works if you have a summation instead of a sum. So step 1, of course, you're going to verify you're going to figure out your dx, and this is nicely done so that you have 1 over n right there. Next, you're going to figure out what is going to be your value of x. And if you take a look at this, you get k over n cubed. So your x is k over n. You got 1, 2, 3. This one's going to 2n because if you look at the upper limit of the summation, you get a 2n up over there. So this is going to go all the way to 2n. Same step 3, you're going to take the first term and figure out what's that limit as n goes to infinity, and you do get 0. Take the second, or the last term, take this limit as n goes to infinity, and you get 2. So now you know you're going to integrate from 0 to 2. Verify that you will actually get a 1 over n as your dx. So you're taking 2 minus 0, and you're dividing by 2n. So that's where all of those numbers come from. If we know that we have k over n cubed here, that means our f of x is x cubed, and our integral becomes 0 to 2 of x cubed. Okay. So let's have ourselves a look at question 1. With question 1, we have this written in not a summation, but as a sum. Okay, what was step 1? Step 1 was to take our sum, factor out 1 over n, because that's our candidate for dx. So we factor out a 1 over n. Notice you get 1 over n squared, 4 over n squared, 9 over n squared over n squared. So that looks pretty good. Just taking a look at this very last term, you can get the idea that f of x is going to be x squared. Okay. Next step that you're going to do is you're going to figure out the x values. Okay, so we've got this is 1 over n, 2 over n, 3 over n, n over n, and x is going to be k over n. Okay, so remember, you're trying to figure out x. You're trying to basically unlink x from f of x. So this part gets a little bit strange. Next step here is to limit the x values. So we're taking our first term, 1 over n, and we're figuring out what is that limit as 1 over n goes to infinity. And you get 0. Take the last x value and take a limit as n goes to infinity, and you get 1. So now you know your integral is going to go from 0 to 1. Let's make sure that our n, our choice of dx, works. And our choice of dx, we're going to take 1 minus 0 and divide it by n, and you do get 1 over n. We're using the n in the denominator because we only have n terms, or the biggest value here is going to be n. So I think that's everything you need to put this together. Here we go. The integral is the integral from 0 to 1 of x squared dx. Caution as you're doing this, question 4 is busted. What I mean by that is this is really a big old typo. Okay, nothing doing with this one, so don't do number 4 at all. We are going to look at number 5 because that does pertain to the rest of the problems. So let's copy down number 5. Here we go. You've got the integral, or the summation of, as k goes from 1 to 2n, 1 over 1 plus 2k over n multiplied by 1 over n. Nicely, they've already factored out 1 over n, so that's going to be our dx is going to be 1 over n. Next thing we're going to do is figure out x. So I'm going to basically say that 1 over 1 plus 2, that's all part of the function. And the only part that's really changing for me is this k over n part. So k over n, as k, when k starts at 1, you get 1 over n. Next one is 2, you get 2 over n, 3 over n, all the way to this very last one, which is 2n over n. Okay. So my x is going to be k over n. Okay, so there's a couple ways of interpreting it. This is the way I'm doing it for now. We're going to look at another interpretation once we move on further. Now that I have my x value, I know x is k over n. I'm going to figure out the limit of the first term as n goes to infinity and the last term as n goes to infinity, and that would be 1 over n and 2 over n. You're going to get 0 to 2. So now you know your integral is going from 0 to 2. Let's verify to make sure we have the correct dx term. So 2 minus 0 over 2n. This is nice to see because you have the 2n up over here, and those two match. 2 minus 0 over 2n, that is 1 over n. So our function is 1 plus 2x. Remember, x over here was k over n. And that's this right here, 2k over n. And now that you have your x, you have your limits, and you have your dx, you can write your integral. This is just the integral from 0 to 2 of 1 over 1 plus 2x dx. Trust me, this isn't easy usually. When we deal with integrals, we usually go through this really quickly because we want to get to the, quote, important stuff. But sometimes this might get you, solve you an extra point or two on your AP test. Who knows? Especially on the multiple choice, you see these kinds of questions almost pretty regularly. Let's move on to question 6. And question 6 basically is what we just did. We're taking question 5 and we're supposing what if x was equal to k over n. Now, as they state in the problem, there is more than one way of doing this problem. So we're going to do number 7 for you. Number 7, we're going to suppose what would happen if we decided that x was actually 2k over n. So taking a look at what we do, or what we did, here's a question one more time. And this time we're going to parse it as 2k over n over here. So we have 2k over n, 1 over n, and that gives us our 1 over n as our dx. We're going to verify that later, of course. Okay, our values of x. Well, this time we're going to take 2k over n, and we're going to say what happens when k is 1. You get 2 over n. When k is 2, you get 4 over n. When k is 3, 3 over n. And when k reaches 2n, you get 4n over n. So this time we're approaching it as x is 2k over n. So it's a slight difference. It took me a minute to figure out exactly what we were going to do with this one. So if you're still trying to wrap your head around it, don't worry, you're not alone in this. Next thing we're going to do is we're going to figure out our upper and lower limits. This part tends to be pretty easy. Let's take our first term, 2 over n, and take that as n goes to infinity. You get 0. Let's take our last term, which is 4n over n, and as n goes to infinity, you do get 4. So our integral is going to go from 0 to 4. Okay? Next, we're going to verify to make sure that we have this correct dx. 4 minus 0, that's 4 minus 0 over 4n, and that is this number up here, 4n. And we get 1 over n. So that is the same one. Identify. So if we have 1 over 2k over n, and we're saying 2k over n is x, that means our f of x is just 1 over x. But notice what did change is over here, we were going all the way to 4 instead of 2. So that gives us our integral from 0 to 4 of 1 over 1 plus x. So that is different. Just take a look at these two. They are different. And that's going to bring us to number 9. Do the integrals 6 through 8, do they integrate to the same value? Well, this one over here, this is going to be equal to, what is this? 1/2 natural log of 1 plus 2x. And when you substitute, well, I better not make that invisible ink, huh? This is going to be equal to the natural log of, sorry, not the natural log, 1/2 the natural log of 1 plus 2x, going from 0 to 2. And if we substitute our 2, we get 1/2 natural log of 5 minus 1/2 natural log of 0, which of course is equal to 1. So 1/2 log 5. What happens if we use, take the natural log here? And now that I'm looking at this, I can see that there's an error here that we made. Down over here for verify dx, let me get this to a highlighter. We have this should have been a 2n to reflect the upper limit over here. And that gives us this extra 1/2. So that's our 1/2 right over there. So our integral is actually a 1/2 over here. So if we're going to integrate this one, again, this is going to be the natural log of 1 plus x and with a 1/2 in front of it. And where is my pen? Hold on. There we go. 1/2, the natural log of 1 plus x from 0 to 4. And when you integrate that, that's 1/2 natural log of 5. Great. Number 9, do the integrals you wrote in 6 through 8, do they all have the same value? And of course, yes, I sincerely hope so. Otherwise, we're creating a problem where two things that are supposed to be equal are not actually equal. So that kind of wraps it up here in 6.2. I feel a little bit uneasy about this because I know that you're probably feeling a little bit uneasy about this. Again, this is a little bit on the tangent on how we create our integrals based on Riemann sums. So, good luck on that, and try to finish up the rest of this, and I'll see you guys next time.